this video, I want to give a brief tour of BB 0.2, and I want to give a lot of credit out to Ben Eater, whose videos I followed when making this. He's now completed his series on building an 8-bit breadboard computer, and so some of the ideas in BB 0.2 aren't what he did, because when I constructed BB 0.2, his videos weren't yet complete. So when I'll explain when we get to that portion of BB, what exactly the problem I encountered and what I decided to do to solve it, because Ben Eater hadn't released his videos and I didn't want to go look at other architectures. Real quick, let's go ahead and start BB off. I believe our clock speed is running at a luxurious 8 Hertz, and it is. We hit Control K. I'm on a Microsoft machine, a Windows computer, and it's loading in the program right now, which in this case is infinite add. It will take a variable and infinitely add whatever number we want. In this case, we have chosen the number 1. And that seems to be going along just swimmingly. So my goal in making this was really just to explore my curiosity about how computing works at the most fundamental level. I found Ben Eater's series of videos and was really surprised and astounded that I could actually understand these concepts, and furthermore that it looked like something I could very reasonably expect to be able to accomplish. The only problem is I don't have any of the equipment to build an 8-bit breadboard computer. I don't have breadboards, I don't have wires, I don't have electrical components, I don't have any of the equipment or supplies or experience you would need to go in and do this project as he does in his videos. I was listening to the podcast that he's a part of called Ben and Blue, and in the first episode he actually mentions, or in one of the first episodes, he mentions that people have followed along with his videos using Logisim. So I decided, why not go ahead and do that? And I've had so much fun with it. It's become quite the hobby for me to continue to build this simulated computer. I'm now on version 0.3 of my lovely computer BB, and 0.2 is complete. It's as done as I'm going to make it. I'm not putting any more effort into it, and I'll release all of the source code for this in terms of the Logisim files that you might need, all the circuit files, and everything like that if anyone wants to play with it. But I'm done developing BB 0.2, and I'm at the place where I've taken the next step to evolving BB 0.3 into accessing the full, or a more full set of features that you would expect from an 8-bit microprocessor today. So all this being said, please give me suggestions and give me tips and advice or your thoughts. A lot of this is very janky. A lot of this is not optimal. I wasn't setting out to achieve optimal, nor was I setting out to become any authority on computing or building 8-bit computers or working with an 8-bit architecture. I'm really just trying to see what I can do myself in solving these problems before reaching out to sources for the solution. So I've followed along Ben Eater's videos, and then when it's come time to actually implement things, I've done my own thing a lot of the times, and I'll point that out along the way. So we do have the ability to perform a conditional jump instruction. So technically this computer is Turing complete, although the amount of memory is exceedingly small. And with that being kept in mind, let's go ahead and take a brief tour. The most important thing to first point out is that my labeling is not quite where it should be. So a lot of this has just been developing over time. These control lines that kind of run around the entire periphery all have a very important part to play, but none of them are really labeled that much. So here we have our clock. The clock sits up here doing its clock thing. It's pulsing 8 Hertz, so 8 times a second the clock is changing states, which means that we are getting 4 cycles of the CPU every second. So it's accomplishing essentially 4 things every second. And the result of this is you can see this wire lighting up in sync with the clock. So this is our clock line. It touches almost every single component. We also have the 8-bit data bus here, and it runs pretty much alongside the clock line most of the time. I've tried to keep that. I've tried to keep the idea of lumping things together. We also have a variety of control lines just kind of strewn about the place. So all the rest of the wires that you see coming out of these wire splitting junctions are lines that come out of the CPU's 32-bit control line. So that 32-bit control line contains every single wire that can do something to one of the components of BB. And as we'll see, this is the means by which we accomplish anything with the computer. And if you want to dive into more of that in detail, either keep watching as I explain each of these components in further videos, or please reference Ben Eater's videos. They're really great references for how to really understand these things on the most basic level. And how to implement them. We have the advantage in Logisim of being able to bundle these wires together, so we have some really neat wiring available to us. So the first place we'll start is the CPU over here. Our CPU is where all of our instructions are being executed. Let's go ahead and switch over, go to Project, and we'll say View Simulation Tree. This will allow us to go into each of the components as the computer is operating and see exactly what everything is doing. And it's just really cool to kind of watch everything happen. So let's go into the CPU real quick. So this is the CPU. It's incredibly simple. It's really just a ROM chip which contains a lookup table. The instruction and the step come into the CPU, and that points to the CPU, and it combines those together into an 8-bit address, which then the CPU spits out whatever data, 32-bit data, is at that address. That 32-bit piece of data at that address lights up with a 1 each of the control lines that needs to go high for the next clock pulse. And then with the next clock low, the instruction is allowed to change. But you can see that the design itself is incredibly simple. There's not a lot going on here in terms of physical wiring or anything like that. So the CPU is where we actually have the control of which components are doing something at any given point in time. So let's kind of branch out from there and look at the various components that make the CPU able to point to instructions. So we have this over here, our instruction register. Our instruction register is an 8-bit register, as all of our registers are. All of them are handmade. I made the individual components from flip-flops down at the lowest level in 1-bit registers, and then chained 1-bit registers together to create 8-bit registers. Logisim has its own built-in register component, which I use in BB 0.3, and I intend to use anytime I'm working in Logisim from now on, because it's the most efficient way to handle this. When you're using, the more registers you have, the more components that the program has to watch out for, and that's really begins to take a toll on the ability of the program to keep up with you. The more stuff you put in, and so that's been a hard limit and has really guided a lot of design decisions. Simply because I don't have the space to just put in as many circuits as I want. So it's a real limitation of the program. So our instruction register, our memory address register, our general register A, general register B, our if register, our jump register, our output register, all of these are based around handmade components. So we can go into the instruction register to sort of see an example of what's going on. So here you see that we have the data bus line coming in, and the instruction register splits out everything into these 1-bit registers. So you see that this data in is the 8-bit bus, and that gets split out into 1-bit signals, so 8 1-bit signals, and then each individual bit is stored in a 1-bit register. If we open up this instruction register, you see we just have 8 1-reg components. That's the custom-made ones that I did following along with Ben Eater. And then we have over here a series of one controlled controlled buffer for each of them. So it's only going to allow the 1-bit registers to output their contents onto the bus if this enable line is high. So when the CPU says, hey, I need an instruction here, it puts that enable line high, and that data is allowed out onto the bus. Whenever it's not putting its contents out onto the bus, as far as the circuit is concerned, it's left floating. As you can see, it really utilized every single instruction. There's a lot of stuff going on that we need the instruction register for. It's one of the most used registers in the computer, so it's putting its contents out onto the bus a lot. While if we go over to register A, it's being used a whole lot less. So you can kind of see the data on the bus over here, the input data. This is what's currently on the bus. There's something on the bus all the time, but it's very rarely the contents of A. So the instruction register is used to point the CPU to which instruction we're currently wanting to execute. But where does that instruction actually come from? That instruction is stored inside of our RAM. So this is the inside of our RAM chip. As you can see, it's composed of 8-bit registers, 16 of them. So inside of each of those is 8 1-bit registers, and you can see that if I wanted to upgrade my RAM, it would require an enormous amount of circuitry, and I did try that once, and it was so much for Logisim that it just couldn't take it. It would take literally 4 or 5 minutes to place a component with I think it was 256 bytes. So it really is impractical to function in this way. But for BB 0.2, because we only have these 16 bytes of RAM, it's manageable, and it actually works, and it works fairly well in terms of performance. There are performance limitations, but I think it's a variety of factors. We can't point at any single one thing. As you can see, I really enjoyed the wiring aspect of this. My wiring is certainly not always neat or the best, but it is fun. I really do enjoy it. So when we take a look at this pretty big component, we have a couple of things going on. First, we have the data line coming in. That's our data bus. We have our data bus out, so that's all well and good. We see how it's connected there. We have our write signal, our enable signal, and our clock. And then we also have the address. So we'll look at where this address comes from shortly. But the address feeds into this decoder circuit. This decoder circuit essentially allows us to input into our write and enable routers the correct information to uniquely identify which of these 16 addresses we're looking at based on the address going in here. Now, this could all very easily be accomplished with a single mux, and I understand that. But the point was to build it from the ground up, and I didn't even know what a mux was at the time. So I kind of hand built my own decoders for this RAM, and it is a lot of fun. So we can actually go inside there and take a look at what those look like. So let's look at the write decoder. Inside of here, we have an address coming in. We have our enable line, so that we're able to be outputting what we're doing here. And really all this is doing is this 8-bit address is coming in, and it uniquely maps, each 8-bit address maps only to one output here. This means that when we have an enable line coming in and an address, we're only going to be putting that enable line out onto the address specified. So then when we come back to our RAM, we can see that when we are enabling to one of these registers to output onto the bus, we only want to be enabling the one here that we're indicating with this address. And the same goes for when we're writing. We only want to write one at a time, and we only want to output one at a time. And we'll look at all of that in greater detail. So that's our RAM. We have all of our program is being stored in here right now. We can actually see the variable which stores here in register 14. We can see memory address 14, we can see the contents of the variable that's currently stored. We're getting pretty high up there. So when we pop back, we'll see how far we've been able to get. So now the question that comes to my mind is, where does this address come from? How do we know which RAM address we want to read or write to, read from or write to? And that is done with the memory address register. The memory address register is just an 8-bit register. It does have an LED out so that we can kind of monitor what's going on at any given time. But what this also accomplishes is when we look at where the memory address register sits, we have that LED out is always outputting whatever's inside of the register, whether or not it's wanting to be put out onto the bus. And that also is tied directly into our RAM. So whatever is inside of the memory address register, the least significant 4 bits of that are being piped into the RAM. So whatever we store in the memory address register, the RAM automatically points to. And then if we have the enable line high, it outputs that value. If we have the write high, it takes the value on the bus and writes it into the address specified. We also have our 2 general purpose registers, registers A and B. We can use those for performing arithmetic with our arithmetic logic unit, which predominantly only does addition and subtraction. And it adds and subtracts whatever's in these registers. So we load up the registers the ALU automatically adds them together or subtracts them together. And then if we want the result of that, we can output that onto the bus, no problem. Ignore this OFU, that doesn't really mean anything. This HDD over here is where we load our program from initially at the beginning of the program. And we'll go into that in much greater detail. This is the jump register. This jump register essentially is where we say, hey, I'd like to jump to this address at some point in the future and now actually do it. When we say actually do it, then the program counter gets reset back to the value in that jump register. So the program counter is what allows us to look at what program instruction we're wanting to execute right now. Every time we want to proceed into the next step of the program, we have to increment our program counter, which then feeds into the memory address register, which then points to that specific place in memory. So at memory address 0 is our first instruction in RAM, and then 1, and then 2, and then 3, and so forth. And we do have to have some room for our data, and this program uses 2 variables, so we need those last 2 bytes of RAM preserved for our own purposes. But if the program counter were to point at memory address 14, where we have that variable which stores that increasing value, it would try to interpret that as an instruction. It would pop out the value of 193, and it would put that in the instruction register, and the CPU would try to execute whatever that would mean. And that's how a lot of errors get caused, is because the wrong data gets put into the wrong place at the wrong time, and things kind of go haywire at that point. Especially when you hit an instruction that isn't defined, a lot of strange stuff happens. So the jump register accomplishes a lot with the program counter. The program counter is an integral component of pointing us to what instruction we're trying to execute right now. The step counter over here, I will not go into in very much detail in this video, but the step counter is the thing that says, given the instruction that's in the instruction register, what step of that instruction are we currently executing? Each assembly instruction is comprised of a multitude of steps. There's some things that almost every single instruction does, and and every instruction has something unique to it that it does. So this step counter allows us to say, given that we are executing instruction 3, say, the step counter starts at 0. So we feed into the CPU, going back to the CPU here, we say, hey, we're on instruction 3, and this would read 3, and then this would read 0. And this is interpreted as these upper most significant bits would read 3, so it would point to that block of memory in the ROM chip here. And then the instruction counter, or the step counter as we call it out on the board, that would increment, say step 0, we're going to execute that, and then now we're going to go to step 1 and execute that, and step 2 and execute that. And at some point, the instruction is done, and the computer knows how to reset back to 0 and say, okay, so now we're going to get the next instruction out of the RAM. We're going to put it into the instruction register, and we're back at 0, and we're going to execute that one. For more details, we'll look at all of that. We'll look at the actual microcode instructions that we're executing and what control lines that lights up in another video. The last thing that I want to take a look at here is the output register, and the output register is here. And the idea with the output register is that you want to output the value. In this case, we're outputting what's stored in our variable. In order to make this efficient, we just have one register. So we place our 8-bit value of 224 in binary in our output register, and it automatically gets decoded in this decoder over here. So this decimal decoder, we'll go into it here. This decimal decoder takes the data that's stored inside of the output register and then pipes it into a lookup table. Just like a lot of things in computing, we have just a ROM chip with a lookup table, and it looks at that value, that 32-bit value, and determines how the control lines that are lighting up the 7-segment displays need to be oriented. Then we take that signal and we split it up appropriately to route it into our actual configuration here, so that it splits up each of the digit values into halves, the upper half and the lower half, and spits them out onto our output display. All the wiring could be cleaned up significantly. I've learned a lot about how to use Logisim more appropriately, so in further videos you'll see that things get cleaned up significantly. But for now, we will live with and embrace the jank of BB 0.2. And that's pretty much it. We do have the if register, but that's a little bit technical. We'll go into that at another time. We have all of these weird things going on here around the step counter and down here by the program counter, whatever this stuff is. So we'll take a look at what all of that is in another video. But this has been a brief tour of BB 0.2. If this is something that interests you, be sure to subscribe and give me a like. And follow along for the next series of videos. We'll be taking an in-depth look at each of these components, as well as talking about how we're going to improve all of these in BB 0.3. So as always, I welcome your questions, your comments, and your suggestions.